This video gives a brief explanation of how to very accurately analyze twin and three-screw compressors, taking into account thermal expansion and other factors. Many other types of compressors, pumps, and turbomachinery can be quickly, easily, and accurately analyzed in the same fashion. Let's get started.
The last one is the FEA capability. This is something, again, we have developed from scratch. It's our native FEA solver. Now we have used it in a few cases, and this is a screw compressor case that we use the capability. So essentially for twin screw compressor, due to gas temperatures rising during the compression process, it can cause higher thermal expansion of the compressor. So this can change the leakage gap, which can be very important because you're pushing air through, and leakages can affect the results quite dramatically. So the way that works now is we have Simerics CFD solver, which is the fluid and the heat transfer model, and that talks to the Simerics CFD solid model, which solves the heat transfer. And this loop keeps performing till we have some flux convergence, and then we go to the structural solver to modify the geometry, and then come back and then do the coupling again. So this is what is explained in this algorithm. So the fluid mesh is about 3 million, the solid mesh is about 0.4 million, and you can see we can model the gaps using our general gear template. It can be essentially, ours is a very unique approach. We brute mesh the entire thing and we squeeze it into a very small gap, all the cells, and still the solver can handle the mesh without any convergence issues, right? This is a pressure contour and a temperature contour. There is no necessity to babysit this process. You will be guaranteed a solution, and you're not going to diverge. This is something that we have done quite a lot of cases with the general gear template, and it's extremely robust. And here you're looking at the solid temperatures and then the rotothermal expansion that is plotted. So once the thermal expansion distribution comes in, we go morph the geometry of the solids as well as the fluid, and then we come back, and this is an automated process that is written using a script, basically. And the resultant of this is essentially the mass flow rate from the simulation, and then we compare that with experimental data as well as the rotor power, and we get favorable results, right? Just to conclude, I think what we have done now in this field is we start with the cavitation physics, which kind of dictates the NPSHR for any pump designing. We have added the acoustics, we have added now the FEA, and now we are coming up with our own CAD kernel. We call it SMP CAD. And that's going to make it a product portfolio which addresses multiple physics, which does it in one platform, and we do it in a robust, fast, and accurate way, which other people can claim, but we have a product that does it